Hello folks, thanks for having me here today. We want to talk about electrokinetic reclamation. And as I get through into this talk, let me boil it down to something simple. Everybody's got a car battery, and you have a positive and a negative terminal. Keep that in mind as I talk, because everything's moving from positive to negative in this talk. The idea of our concept came up about 5 years ago when we were looking at ways to reinvent ourselves in the environmental remediation market, nothing to do with reclamation. But we came up with the recognition that there was a big problem with tailings, especially tailings in Alberta and around the world with expansive clays. Anything that has an expansive clay, MFT certainly has kaolinite, there are bentonites, other types of smectite expanding clays, were ones that we thought we could probably use electricity to take the water out of the slurry and compact the clay. And that first concept work started in 2010 with Dr. Krishna Reddy at the University of Illinois, Chicago, where me and my colleagues had worked with him in the 80s and 90s to look at ways that we could use high temperature thermal electricity to dewater solvents off of groundwater tailings, groundwater regimes. And the first work that was done there was with AT&T at the Skokie Works. We proved our idea, and he said, well, boys, you're going to have to go back to the laboratory and figure out how you're going to keep your costs down, because everybody knows that electroosmosis using direct current has been very successful in dewatering hillsides, but it's expensive technology, and you tend to burn up your electrodes. So what we were able to do in our test work in Escondido, which is in San Diego, is come up with a concept of mixing alternating current with direct current in such a way that we preserved our electrodes, still moved water out of the clay mixture, and were able to keep the cost down. Once we had gotten that done in small 1 and 5 liter test sets to 30 liter, we then said, well, we need a partner. We need to take this to somebody up in Alberta who can help us get more MFT and move to the next scale. And 2 people definitely stepped up. That was Rick Nelson with AI-EES and Gavin Freeman with Shell. And from 2012 to 2013, they helped us work with tote testing and other designs in Escondido to verify our concept and to set us on the path of commercialization. And since 2014, that's what we've been working on. It started with the real breakthrough was at the 1,000 liter level, where we had a tote of Shell Albion material, about 38–40% MFT solids concentration. And we were in a period of about 14 days able to reduce this to the numbers that you see there with significant shear strengths. Now, if you look at the picture, what you're seeing is in the center is a cathode, and at the 4 corners, north, south, east, and west, are anodes. Those are the stainless steel cabling that you see. And we were able, when we were designing this, to make the cathode pump water. As the electricity moves from anode to cathode, from your positive to negative, not only was water expressed from the MFT up to the surface, but also through this pumping cathode. And that told us a lot about commercial scale and design work. The next question that we were asked by Rick and Gavin was, okay, how about vertical electrode space? What can you guys do? I mean, you can't porcupine an MFT pond with electrodes. You're going to have something that's reasonable in size and scale. So what we built was an acrylic tank test where we took 1,000 liters of MFT. It was basically a 2D test. And on the right side is the anode, and on the left side is the cathode. And we ran this for 7 weeks. And the result is you can see how the mud line dropped. We keep the electrodes only in the mud line, not in the water. We created a water cap. And what was really interesting, if you look on the right side, you see that shaded area. What that is actually buildup of solids that's pulled itself off the acrylic wall. And we also, on the left side, where the cathode is, we also saw a significant amount of solids buildup. So then we realized that our picture from the 3D and the tote to the 2D proved out that at 5-meter spacing, we continued to sequester solids and express water, and especially around the electrode array. So now the question came up, well, how do you guys plan to vision this for commercial scale? Well, again, with the 5-meter test success, we realized that N-Pit Lake certainly could be a location where we could put electrode arrays in the mudline, not in the water, power them, and extract the water suitable for bitumen reuse, and have a consolidated material that you could leave in place. The next vision we came up with was, well, how would you deal with something, let's say, in an existing pond? And we started work on the electrode array designs. How could we do a vertical? How can we do a horizontal? How can we do a combination hybrid of those two that would be effective and efficient? Then we came back to the question of, well, now we need to test that at larger scale. We also need to test in cold weather. At the same time, we were working on a mathematical model to predict how much water we would generate based on how much power we put into the system, and that has helped us design the power gradient necessary for scale-up testing. So in 2014, thanks to Rick, he introduced us to the folks at CEFR Technologies in Edmonton, and we were able to lease space in their brand new facility and build ourselves a 130-meter fiberglass tank to test our hybrid array. Now, the hybrid array is a combination of the 2D that you just saw, but in 4 dimensions, and the idea being that we would have both vertical and horizontal electrodes so that we would have overlapping power gradients, so we would have a constant power gradient movement through the MFT medium and reduce wet spots that could occur between the anode and the cathode. So we had a more homogeneous type of material. And that was key to the questions we were being asked by Shell. Another test that we were asked to do is an outdoor test where we could just do the horizontal arrays. The horizontal arrays, unlike the deep formations, would be in shallow formations and subject to freeze-thaw. So we were very interested in that, so we took a Baker tank, a frac tank, and designed it to our needs. And here at the CEFR facility, you see that on the right, at the top right, that was the 130-meter fiberglass tank with the electrode array deployed. Then we filled it with the shell material, which you see on the left, as well as underneath the Baker tank filled and outside the CEFR facility. On the lower right is a typical modular unit of our power. All our power units were designed to be robust, to work in outside conditions or inside conditions. They're automated, they run by computer, and we can tap in from the internet to make changes in our configurations as needed. All of these are ideas that we had to put in play to convince folks that we were ready to go commercial. So the metrics of success for our testing at CEFR were to get past 60% solids, recover water suitable for bitumen recovery, power costs somewhere in the $15 to $30 a dry ton, and prove that the system works at a tank scale with as well some information on how freeze-thaw would impact it. So consumed power in the 130-meter test, as I told you, we have our model, which is in blue, and in brown, you see the cumulative power that goes through that 335 days of operation. Water released followed a similar pathway, and things start slow in our process at first, and as the water content is reduced, then things pick up towards the back end of our test procedure. And we see that again with the solids formation, starting at 35% up to 60%. It's a slow go for the first 2/3 of the year. The last third, as the water separates out and the slurry becomes more of a soil, the production of solids increases dramatically. Treatment costs as well start low, but then opposite of that, they plateau. And right now we're in the $11 a dry ton range, well within our budget on the 130-meter tank. The 25-meter tank, this is a picture of it pumped down with the water cap now removed after 330 days of treatment. And we have a very solid-looking material with some areas here that had very high KPAs, others that are a little wet as it's still drying out. But if you think of this as subsurface at the bottom of a treatment pond, this would be easy material to take another lift of MFT on top of it and treat again, and this would only get harder. So the treatment results with the 25 meter, including 12 to 13% of freeze-thaw contribution we learned, we still were able to get approximately 60% solids in the same period of time. A little bit higher in cost, but within our budget. So what are our next steps? Our next steps are to continue treating the 130-meter tank until December. We'll break it down in January and do a forensic detailed analysis of it. We're going to work with John Sopkowitz and of Thurber and have him do an independent analysis of our results and then publish that in our paper. We're going to get that out hopefully by February 2016. And right now we're working on a full-scale field deployment with a CASIA member that we hope to splash a hybrid array up in Fort McMurray by July, August next year to run for a full year underneath the ice cap and see what results we can get at full scale. So it's been very exciting. The work continues. The price point is correct. We're very cost competitive. We're getting water extrapolated that's good for bitumen reuse, and we're getting great solids formation around the electrode arrays at the layers that we're treating in.